Hi, welcome to lecture 23. This topic of this lecture is Hensel's lemma. Lecture 23, the topic is Hensel's lemma. This is a periodic version of what you might have seen in calculus, what's called the Newton-Raphson method. So let's start by recalling this method from calculus. And the motivation for this method is you want some sort of geometric process which is iterative to approximate roots of a function f of x. Okay. So this function has to be nice in some sense, but I'll just sweep that assumption under the rug. So what you first do is you draw this graph. So you draw the graph of y equals f of x. So suppose for simplicity it looks like this. And let's say it has these two roots, beta and alpha, and somehow you want to compute one root of this function f of x. And so the process is, let's say you start with an arbitrary approximation. Say x equals a naught. Okay, so you really want to find alpha, but maybe the function is complicated that you don't have a handle on the root. So let's say you just begin with some random a naught. And what's this process? Now you compute the corresponding point on the curve. Compute the point on the curve. So you plug in x equals a naught, and then y is f of a naught. So you get this point on the curve, a naught, comma f of a naught. And then what you do is you just draw a tangent at this point and see where it intersects the x-axis. So draw a tangent at this point. So let's say something like this. And let's say it meets the x-axis at another point a1. So the equation of this line, the equation of this tangent line, again just from calculus, is one of the y coordinates is f of alpha naught or f of a naught. So here y minus f of a naught equals f prime of a naught times x minus a naught. So the new x-intercept a1, just plug in y equals 0 and solve for a1. a1 is a naught minus f of a naught over f prime of a naught. Okay, and now you just repeat the process. So again you try to compute where this a1 meets, pardon my drawing. So now you try to find where a1 meets the curve. So you get this new point a1 f of a1, and now you try to draw a tangent line from there. Then you get this new point a2, and then you just repeat this process iteratively. And then you see that you get closer and closer to this root alpha. And you also might observe that if you start with another point that's close to beta, so let's say you start with a point that's close to beta, and you try to repeat this process. So you get this point a naught f of a naught, you draw a tangent, you get a1, then get this new point a1 comma f of a1, and so on and so forth. Okay. So I guess one observation is that depending on the initial approximation or starting point, this process could lead to different roots of f of x equals 0. And again, the success of this process really depends on the initial function and so there are conditions on derivatives of this function, and so the point is that you need to assume nice smoothness hypothesis or smoothness properties on f of x. Okay, so this is the Newton-Raphson method, and our goal is to consider similar method to solve for roots of, well, I won't consider a general function, I'll just consider polynomials f of x, where it's a polynomial in one variable and the coefficients are in ZP. So I have a polynomial in one variable and the coefficients are periodic integers. Okay. And so maybe before stating Hensel's lemma, so the analog of Newton-Raphson method in the periodic case is called Hensel's lemma. So before stating that, just a few formal properties. Of polynomials f of x in Zp of x. You can usually one considers this expansion at 0, but you can just write the expansion of the polynomial centered at any random point. So let's say it's centered at some point, say a. So you write f of x equals f of a plus c1 x minus a plus c2 x minus a square, and so on and so forth, and assume it's a degree d polynomial, so cd times x minus a raised to d. Okay. So in particular, suppose I'm only interested in the first derivative, I'll write this as f of x equals f of a plus c1 x minus a, and I'll just collect all the higher order terms, so I'll write this as x minus a square times, let's say, h0 of x, where these, so all these ci's are in Zp, and so again c1 is in Zp, and this h naught is a polynomial in one variable over Zp. Okay, so what's C1? You can also consider the formal derivative. F prime of x. So that starts with C1 plus C2 x minus a plus again so on and so forth, d times cd x minus a raised to d minus 1. And so again f prime of x, the constant term here is f prime of a, And let's write this as x minus a times h1 of x, where this h1 of x is again a polynomial in one variable over zp. Okay, so just some formal properties that you're already aware of for polynomials. So we'll need this later in the proof of Hensel's lemma. And again, before the proof, just one more lemma. So suppose we have a sequence, say an, that these ans are in Zp, with the property that for all numbers n, an plus 1 minus an, this is less than equal to 1 over p to the n plus 1. Okay. So if you have such a sequence, then the sequence an is a Cauchy sequence in Zp, and let's just say that alpha is the limit of this Cauchy sequence, and what we also have is that if you take the initial term, let's call it a naught, and take its difference with alpha, the periodic absolute value of this difference is strictly less than 1. Okay. So again, this proof relies on the fact that we are working with the periodic absolute value. So for all m larger than or equal to n, what do we have? I want to compute the difference of, let's say, am and an. Again, you play this trick of adding and subtracting terms. So let's say am minus 1 plus am minus 1 minus am minus 2, and so on and so forth. You go to an plus 1 minus an. And so if you want to compute the periodic absolute value of the difference between am and an, you collect terms two at a time. So you have am minus 1 plus am minus 1 minus am minus 2 plus so on and so forth, an plus 1 minus an. Okay. So the hypothesis that I have is that if I take two successive terms, take the difference and compute the periodic absolute value, that's less than equal to 1 over p to the n plus 1. So I've grouped these terms together, and so now I have a handle on the periodic absolute value of these differences. So now if I just use the ultrametric property, or rather an inductive form of this ultrametric property, we have that the difference am minus an in periodic absolute value is less than equal to the maxima of, take the difference of am minus 1 in periodic absolute value all the way up to an plus 1 minus an in periodic absolute value. And so now observe that for each I between n and m, I look at each of these terms. I want a handle on the periodic absolute value. So if I take the difference ai plus 1 minus ai, by hypothesis this is less than equal to 1 over p raised to I plus 1, but I is larger than or equal to n, so this is less than equal to 1 over p raised to n plus 1. So each of these terms here in periodic absolute value less than equal to 1 over p raised to n plus 1. And so again, by the ultrametric property, we have that am minus an in periodic absolute value is less than equal to 1 over p raised to n plus 1. And this is true for all m larger than or equal to n. And so this shows that the sequence am or an is a Cauchy sequence in Zp. Okay. and in particular, since Zp is the periodic completion of Z, it is complete with respect to the periodic absolute value. So we have a limit alpha in Zp, that is alpha equals this limit n goes to infinity of an. Okay. Now again, if you stare at this inequality and you just apply this inequality for n equals 0, we get that for all m larger than or equal to 0, we have am minus a0 in periodic absolute value is less than or equal to 1 over p. So in particular, if you take the difference between alpha and a naught, and again you play the same game of adding and subtracting am, and applying the ultrametric inequality, what you have is that the difference between alpha and a naught in periodic absolute value is less than or equal to the maximum of alpha minus am in periodic absolute value and am minus a naught in periodic absolute value. Okay, and this is true for all m. Now the second quantity we've just shown, that is periodic absolute value is less than or equal to 1 over p. Since alpha is the limit as m goes to infinity of am, you just choose m so that alpha minus am is also less than or equal to 1 over p. So you choose a large enough m so that the first quantity is also less than or equal to 1 over p, and so in particular alpha minus a naught in periodic absolute value is also less than or equal to 1 over p, which is strictly less than 1. Okay, and so this completes the proof of this lemma, this intermediate lemma. So now we can move on to Hensel's lemma, which I'll state as a theorem. This is theorem 52, also sometimes called Hensel's lemma. So you start with a polynomial in one variable over Zp, and suppose you can find an initial approximation, an initial good root, and what does that mean? So you take an alpha naught in Zp and suppose it satisfies some nice condition. So the first condition is that, so I really want f of a naught to be 0, but maybe I don't know that it's 0, but I know that it's 0 modulo the maximal ideal. Okay, so this is my initial approximation. So what does that mean? That is, f of a naught belongs to the maximal ideal p Zp. And another way of stating that in terms of periodic absolute values is that if I evaluate f of a naught and compute its periodic absolute value, this is less than or equal to 1 over p, which is strictly less than 1. Okay, so if I have an initial approximation and I need some analog of the smoothness hypothesis, so I need some condition on the derivative. So if I take the derivative of f and evaluate it at a naught, then what I have is that this is not 0 mod p. Okay, and again what this means is that the derivative f of a naught does not belong to p Zp. And again in terms of absolute values, periodic absolute values, what that means is that if you take the periodic absolute value of f prime of a naught, this is equal to 1. Okay. So suppose you're given these initial conditions, then you can find a root of this polynomial that's unique. So you have a unique alpha in ZP that's a root of f, and it's related to this initial choice A naught in the sense that alpha minus A naught in periodic absolute value is strictly less than 1. Okay. So this is Hensel's lemma, and let's try to prove this. And so again we want to use this motivation or intuition from Newton-Raphson method. We want to define a sequence. So we want to define a sequence, so analogous to the Newton-Raphson method. So again, if you go to the Newton-Raphson method, so we had this geometric picture, but then we also had this sort of algebraic formula. So if you give me an approximation A naught, I could construct A1. If you give me A1, I can construct A2. If you give me A2, I can construct A3. So you have this purely algebraic description of this geometric process. So this is what we'll use. So we define a sequence. So for all n, we define an plus 1 equals an minus f of an divided by f prime of an. So I have this sequence, and to complete the proof of Hensel's lemma, I want to establish some properties for the sequence. So my claim is that if I look at f of an and compute its periodic absolute value, this is less than or equal to 1 over p to the n plus 1. If I take the derivative of f and compute it at an and compute its periodic absolute value, this is 1. And then if I look at an plus 1 minus an and compute the periodic absolute value, this is less than or equal to 1 over p to the n plus 1. Okay. So I have the sequence analogous to the Newton-Raphson method, and I want to establish some properties about the sequence. So these properties are summarized in this claim. So we'll prove this claim by induction. Okay, so we have the statement n. So these three statements that I'll just repeat. One's about the periodic absolute value of the evaluation of f. One is about the periodic absolute value of the derivative. And one is about the periodic absolute value of the successive differences of the approximations. Okay. And so what's the base case? Statement n equals 0. So you see that 1 and 2 hold, since by hypothesis we have that the periodic absolute value of f of a naught is less than or equal to 1 over p. This is part of the hypothesis. And another thing that was part of the hypothesis is that the derivative, if you look at the derivative f prime of a naught and compute its periodic absolute value, this is equal to 1. So statements 1 and 2 for n equals 0 is just part of the hypothesis. Now for statement 3, or the third statement in this claim, so you have a1 minus a naught. And again by the formula, this is f of a naught divided by f prime of a naught. So if you look at the periodic absolute value of this difference, this is nothing but f of a naught in periodic absolute value divided by the derivative at a naught and computing its periodic absolute value. But the periodic absolute value of f prime of a naught is 1. So this expression out here is just f of a naught, the periodic absolute value divided by 1. but the periodic absolute value of f of a naught is less than or equal to 1 over p. So this expression is less than or equal to 1 over p, and I'll just write this as 1 over p raised to 1. So you see that this third statement 3 is also true in the base case. So we verify the base case. So we've verified the base case, n equals 0. And so now assume that the case holds for n. So now assume that statement, say n holds. So what we have is that the periodic absolute value of f of a n is less than or equal to 1 over p raised to n plus 1. We have that the periodic absolute value of f prime of a n, this is 1. And what we have is that a n plus 1 minus a n in periodic absolute value is less than or equal to 1 over p raised to n plus 1. Okay, so this is given to us, and what we want to show, is that statement n plus 1 holds. That is, if I look at f of a n plus 1 and compute its periodic absolute value, this is less than or equal to 1 over p raised to n plus 2. If I compute the derivative at a n plus 1 and look at its periodic absolute value, that's 1. And the third thing that I want to show is that if I look at the difference between a n plus 2 and a n plus 1 in periodic absolute value, this is less than or equal to 1 over p raised to n plus 2. Okay, so these are the three statements that I need to show. Now for the first statement, I look at the expansion of f of x around a n. So around a n, the constant term is f of a n plus f prime of a n times x minus a n plus x minus a n square and some polynomial h of x, where this h of x belongs to zp of x. Okay, and now if you plug in, say x equals a n plus 1, what do we get? We have f of a n plus 1 equals f of a n plus f prime of a n plus 1 minus a n plus a n plus 1 minus a n the whole square times h of a n plus 1. Now, what's the formula for a n plus 1 minus a n? Now, if you look at the formula, a n plus 1 minus a n is just this negative f of a n over f prime of a n. So substituting this expression back out here, what do we get? We get that f of a n plus 1 minus f of a n equals f prime of a n. And now substituting this expression back, we get minus f of a n divided by f prime of a n. Okay, plus a n plus 1 minus a n square times h of a n plus 1. Okay, so maybe I'll just write this f of a n on the other side. So I'll leave f of a n on the right hand side. And so simplifying, we get that f of a n plus 1 equals f of a n. And for this next term, if you cancel the denominators, you get minus f of a n plus a n plus 1 minus a n the whole square times h of a n plus 1. So you see that f of a n and negative f of a n, they cancel off. And so what we get is that f of a n plus 1 equals a n plus 1 minus a n the whole square times h of a n plus 1. Okay, and now since h of x is a polynomial over zp in one variable, So when you plug in x equals an plus 1, you get a polynomial expression over zp, but an itself is in zp, so you get that h of an is also in zp. And so in particular, its periodic absolute value is less than or equal to 1, since these an's are in zp. And so if you now compute the periodic absolute value of f of an plus 1, this is, you take the difference between an plus 1 and an, compute the periodic absolute value, take its square, and then you have the periodic absolute value of h of an plus 1. But now by the induction hypothesis, we have that an plus 1 minus an in periodic absolute value, this is less than or equal to 1 over p raised to n plus 1. So using this third statement here, what we get is that the periodic absolute value of f of an plus 1 is less than or equal to 1 over p raised to n plus 1, the whole square, times 1. And so this expression on the right hand side is 1 over p raised to 2n plus 2. And so this is less than or equal to 1 over p raised to n plus 2. Okay, so this gives part 1 of statement n plus 1. And for part 2, you look at the expansion of f prime of x around an. So you get f prime of x is f prime of an plus x minus an times some polynomial, say h1 of x, where this h1 of x is in zp of x. Okay, and just as earlier, now if you plug in x equals an plus 1, we get that f prime of an plus 1 is f prime of an plus an plus 1 minus an times h1 of an plus 1. Okay, and again, going modulo this maximal ideal pzp, what do we have? We have that an plus 1 minus an is congruent to 0 mod pzp. And why do I know that? Because by the induction hypothesis, if I take the difference and compute the periodic absolute value, this is strictly less than 1 by the induction hypothesis. Of statement n. Okay, so on the one hand, this third expression here, this is congruent to 0 mod pzp. And so what this means is that f prime of an plus 1 is congruent to f prime of an modulo pzp. Since by the induction hypothesis again, this is now part 2 of statement n. We have that f prime of an and periodic absolute value equals 1. That's the same thing as saying that f prime of an does not belong to pzp. And so now using the fact that f prime of an plus 1 is congruent to f prime of an, since f prime of an does not belong to pzp, this means that f prime of an plus 1 also does not belong to pzp. And another way of stating that is that in terms of periodic absolute values, the periodic absolute value of the derivative at an plus 1 equals 1. And so this proves part 2 of statement n plus 1. And now for part 3, look at an plus 2 minus an plus 1. Now by definition this is f of a n plus 1 over f prime of a n plus 1. And so now if you take the periodic absolute value of this difference, now we have the periodic absolute value of the numerator over the denominator. We've just shown that the periodic absolute value of the denominator is 1. So the denominator is just 1. And we also shown that the numerator by part 1 has the periodic absolute value of f of a n plus 1 is less than 1 over p raised to n plus 2. Okay, so this first equality here is by part 2 that we've just shown, and the second inequality here is by part 1. And so this observation proves part 3 of statement n plus 1. And so by induction we have proved the claim. Okay, so in particular by part 3 what do we have? That a n plus 1 minus a n in periodic absolute value is less than equal to 1 over p raised to n plus 1. And so by lemma 51 that we just shown, the sequence a n is Cauchy, and say that alpha equals this limit of these a n's. And we also have by the same lemma that alpha minus a naught in periodic absolute value is less than equal to 1 over p, and which means it's strictly less than 1. And again, since alpha equals the limit as n goes to infinity of a n, this means that alpha to the I equals limit of n goes to infinity of a n to the I for all I larger than or equal to 0. Okay. Now by part 1 we have that the absolute value of the periodic absolute value of f of a n is less than or equal to 1 over p raised to n plus 1, and so this just means that the limit as n goes to infinity of f of a n equals 0. Now what's f of x? Suppose you write f of x as c0 plus c1x plus c2x squared plus ci xi all the way up till cd x raised to d. F of a n equals c0 plus c1 a n plus c2 a n squared, and so on and so forth. And just taking limits, the left hand side is the limit as n goes to infinity of f of a n, which by the induction hypothesis we show that that equals to 0. But the right hand side is just f evaluated. So you see that an arbitrary term here is the limit as n goes to infinity of ci a n to the I, but that's just alpha to the I, ci alpha to the I. So you just get c0 plus c1 alpha plus c2 alpha squared plus ci alpha to the I, and so on, cd alpha to the d. So in fact what you get is that f of alpha equals 0. So we get that f of alpha is 0, and by construction alpha minus a naught is strictly less than 1. Okay. So we obtained a root alpha of f of x, that is f of alpha equals 0, with the property that its distance from A naught is strictly less than 1. Okay. So what's left to prove? Is the uniqueness assertion. So a root that satisfies this property that it's close to A naught. So we still have to prove that that root is unique. So what's left to prove is the uniqueness assertion of Hensel's lemma. Okay. Before proving the uniqueness assertion, observe that, you know, if you look at f prime of alpha, you can write this as, well, f prime of A naught plus alpha minus A naught times some polynomial, again, I'll just call it h1 again, h1 of alpha. So what we have, so we've just shown that since the absolute value of alpha minus A naught, the periodic absolute value is less than 1, this means that alpha minus A naught is congruent to 0 modulo PZP. Okay. On the other hand, we have that f prime of A naught, this is not congruent to 0 mod PZP. Okay. So in particular, since we observe that the second expression on the right hand side that's congruent to 0 mod PZP, what we have is that f prime of alpha is congruent to f prime of A naught modulo PZP. And now since the absolute value of f prime of A naught, the periodic absolute value of f prime of A naught equals 1, this implies that f prime of A naught does not belong to PZP. So again, by this congruence that f prime of alpha is congruent to f prime of A naught modulo PZP, what we get is that f prime of alpha does not belong to PZP as well. And so another way of saying that is that the periodic absolute value of f prime of alpha equals 1. Okay. So we'll use this hypothesis to prove the uniqueness assertion of Hensel's lemma. So suppose you have a beta that's not equal to alpha, and this is another root of f of x with the property that it's also close to A naught. So beta minus A naught in periodic absolute value is less than 1. Okay. So the question is, can this happen? So suppose for the sake of contradiction that we have this other root, then if I compute the periodic absolute value of beta and alpha, beta minus alpha, then again playing the same trick of adding and subtracting A naught, and using the ultrametric property, you see that this is less than equal to the maximum of beta minus A naught in periodic absolute value and A naught minus alpha in periodic absolute value. Okay, but each of these quantities by hypothesis, so the first one by hypothesis is less than 1, and the second one by construction is less than 1. So what we have is that the distance between beta and alpha, so the periodic absolute value of beta minus alpha is also strictly less than 1. Okay, so how do we use this? So if you write down the expression for f of x centered at alpha, so f of x equals f of alpha plus x minus alpha f prime of alpha plus x minus alpha square times, say, some g of x for some g of x. It's a polynomial in one variable over zp. And now if you plug in x equals beta, we get that f of beta equals f of alpha plus beta minus alpha times f prime of alpha plus beta minus alpha square times g of beta. And now since alpha and beta are roots of f, we have that f of alpha equals f of beta equals 0, since alpha comma beta are roots of f of x. And so if you simplify this expression above, what do we get? We get that f prime of alpha times beta minus alpha equals minus beta minus alpha square times g of beta. And so since beta is not equal to alpha, you can divide by beta minus alpha, and you get that f prime of alpha equals minus beta minus alpha times g of beta. Okay, so we've just computed that the periodic absolute value of the left hand side, that equals 1. So we've just computed that earlier, that the periodic absolute value of f prime of alpha equals 1. So using this fact, we see that the periodic absolute value of the left hand side equals 1. But if you compute the periodic absolute value of the right hand side, you get beta minus alpha times g of beta. And again, since g of x is a polynomial in one variable over zp of x, if you evaluate it at beta, which is in zp again, the periodic absolute value is less than or equal to 1. We've just seen again earlier that if you look at the difference beta minus alpha and compute the periodic absolute value, that's strictly less than 1. So using that, you get that the second or the first quantity here, beta minus alpha in periodic absolute value is strictly less than 1. So you see that the periodic absolute value of the right hand side is strictly less than 1. So we have that 1 is strictly less than 1, that's a contradiction. So the only possibility is that the uniqueness assertion of Hensel's lemma holds. Okay, so this completes the proof of Hensel's lemma. Okay, thank you.